Good morning, everyone, to the second session of the morning. In this session, we'll have all on-site speakers. Fabrice Bert, followed by Sanjeev Kumar. And let's welcome Fabrice. He's going to talk about the recent developments that are taking place in our understanding of new Kagome systems that, that have come up. It's going to be Y-kapellasite, which has seen a lot of activity over the recent past. And he'll tell us about the long-range order and the distorted Kagome lattice of this system. So welcome, Fabrice, and we look forward to your talk.
Okay, thank you. Good morning to everyone. I'm Fabrice Bert from Université Paris-Saclay in France. And so first I would like to thank very warmly the organizer for this very nice conference. And I appreciate to be back in India after a very long time, and I really enjoy this ICTS conference and the center itself. It's a very peaceful place and a very nice place close to the busy Bangalore. So I'm very happy with that. So today I would like to present actually indeed very recent results that we obtained in this rather new compound Y3Cu9, which actually present distorted Kagome lattice. And I will discuss more specifically, well, this compound, the new model it relies, and the magnetic order that we observed. Does it work? Yes. So this is the outline of the talk. So I will briefly reintroduce Kagome physics. Then I will spend more time describing this new Y3Cu9 and its structure and the magnetic model we can infer from the structure. And I'll go to recent results about the structure and the distortion issues in this material. And finally, to the main topic, which is the magnetic order that we observe and that we can compare to theoretical prediction. So these are the nice crystals we've been working on, and the new model of this compound. Okay, but before going to that, let me thank my collaborators. So the project was really initiated and is supported by Pascal Pufal at Stuttgart. Well, from the start, it did grow first powder, then a very single crystal, then now very nice large single crystals, and doing many experiments also. I would like obviously to thank my colleagues in Orsay, and in particular, this is Dipranjan-Chatterjee. That's the main topic of Dipranjan-Chatterjee, and what I will show is mainly from him. Quentin Barthélémy was former PhD who initiated the measurements and is now in Sherbrooke. And my long-time collaborators, Philippe Mendels and Edwin Kermarek. Edwin did most of the neutron measurement that I will show. And there are actually many people, other people involved at different stages in the study. For instance, Andrei Pustogov, Sylvain Petit, Stéphane Chouelot, etc., who did either some measurement or analysis. And on the theoretical side, there have been parallel study, I would say. The experiment and the theory have been feeding each other on the subject. And actually, most of the authors are, well, some of the authors are at the conference. So we have Harald here in the audience. You heard Roser Valenti yesterday, and Johannes Reuter unfortunately could not make it, but was supposed to participate. So I will obviously discuss a lot these theoretical results and to compare with our results. Okay, so let me remind you a bit of the Kagome physics. So at this you heard already a lot of these arguments during the beginning of the week. Let me just remind you why the Kagome lattice is so special, and even at the classical level. So it's a frustrated lattice. It's based on triangles. But so I'm discussing here the pure Kagome model with nearest neighbor Heisenberg antiferromagnetic interaction. Okay. So it's frustrated. It's what we call highly frustrated because of a low coordination, and the manifestation is actually macroscopic degeneracy of a ground state at the classical level. And not only is there a macroscopic degeneracy, but all these ground states are actually connected, and so there's a continuum of ground state, and you could represent it like behind the black square here. You can represent it in some phase space as a continuous line that connects all these ground states. And one way to go from one ground state to another is to go through such kind of soft modes, which are really soft modes, which are really zero in energy, because when you do such movement of the spin, you respect the condition that the sum of the spin on each triangle remains zero. Okay, so that's what in the early days gave the name of spin liquid, the equivalent of a liquid state at the classical level. So obviously there are other mechanisms that may at the classical level induce order. There are subtle order by disorder effects, etc., but I don't go into that. So with such exotic physics at the classical level, we can expect interesting quantum phenomena that you've heard about already, and that's not the subject of the talk, so I will not spend too much time on that. But just to remind you that it's a hard problem. We know there's no long-range order. It's probably some kind of spin liquid in the ground state, but we don't know which kind. We don't know what is the nature of excitation. Maybe it's a gapless spin liquid, but it's still ongoing work. So that's a very hard problem. And as an experimentalist, what can you do? So there are two main strategies. So first one is to attack the problem directly and to try to get the best ever realization of the model. And that's actually what people do, including us. Looking, for instance, at very good realization. Fortunately, there are good realization of this model, which are like Herbert-Smithite or Singh-Barlow-White that you heard about yesterday, well, so some day before. And you will have a talk on Herbert-Smithite next week. And you try to understand the properties of the system. They indeed show some signature of spin liquid. Now it remains also on the experimental side quite challenging to understand exactly which kind of spin liquid it is, to extract the intrinsic physics, and the nature of excitation is not obvious in a context where there is not much theoretical prediction, let's say, or too many theoretical prediction. And okay, so that's not what I'm going to do here. The other way around is to try to have a sideways look on the problem and to look at maybe a more general problem, maybe to try to extend the phase diagram, and in a more general phase diagram where the Kagome, isotropic Kagome problem would be a single point, let's say. So while doing that, first motivation is that many materials are not good realization of the Kagome model, and still they show interesting physics and new states, etc. So there is new physics. I will show you some example that can be found in a non-perfect model. And if we are lucky, you could even imagine to get some feedback on the Kagome problem itself by taking this side route. So let me give you a few examples of distortion that we could imagine. So there are harmless distortions, such like in this breathing Kagome, where you can think of allowing for two different sides of the triangles. And this is actually realized in this material that we have been studying. Magnetism is from vanadium here, and which has triggered theoretical work. And it's actually very interesting. The Kagome physics seems to be very stable up to large breathing ratio. You can think of adding further neighbor interaction, as it was the case in this compound Y-kapellasite, where it turned out that the first nearest neighbor was actually pretty small and even slightly ferromagnetic. And the other component, the other interaction are important, and they define a very large phase diagram with interesting phases like chiral phases, etc., which are still under investigation. Another way, which is a bit more drastic, is to imagine models with anisotropy of the exchange. I mean, nearest neighbor interaction, but which are different on the bonds, on the free bonds on one triangle. So now we don't have any more perfect triangles, but triangles with maybe two different exchanges or maybe even three. Okay. So that was a model proposed at some point to explain, for instance, Volbortite. So you may end up with, so usually when you do that, you tend to go to long-range order quite easily. Now the model so Volbortite, it's quite interesting. It's actually the first quantum Kagome material that was discovered in 2001. It was made by Zenji Roy, and it's still under investigation. There are still interesting phases, physics under magnetic field, etc. And the description of the magnetic model has evolved a lot. But okay, the starting point was exchange anisotropy. So the yttrium-kapellasite somehow falls into this kind of category, and I will now tell you more about it. So for the history of this material, actually the initial motivation was to try, knowing that zinc-Herbert-Smithite was a rather good realization of spin liquid, or the best we had. The idea was to try to charge dope it and try to get to a metallic state. So you heard about Kagome metals on Tuesday, I think. And you could expect Dirac physics, flat band physics, Van Hoff singularities, related physics, etc. You could even imagine superconductivity out of the spin liquid when it's doped, etc. So there's a lot of motivation to do that. Actually, so far, all the attempts failed, including this one. So somehow the system managed to incorporate this additional charge and stays insulated. But the positive outcome is that we ended up with two new structures. So the compound, basically, when you try to substitute zinc by yttrium, the structure changes. So from the structure of Herbert-Smithite, you go to the structure of kapellasite. It's also a Kagome structure with a simpler stacking, actually, and a 2D, more 2D structure. And you end up actually with two new structures, which are so-called x equals 0 and x equals 1/3, and I'm going to explain a little bit what it is. So the x equals 0 material, it's actually a perfect Kagome. It shows a perfect Kagome lattice. For both compounds, since yttrium and copper are very different ions, you don't expect, and we don't get intersite mixing on the two sides. So the copper layer should be rather perfect. And so this material, so it's a perfect Kagome lattice, and actually it freezes at 15K to long-range order in a Q equals 0 structure that was understood as results of a large Jelosinski-Moria interaction below the critical value that stabilized long-range order. And so I'm not going to talk very much. We did the initial study on powder sample of this one in this paper, but it was mostly studied by Andrei Zorko here. And so if you have questions about it, you can ask him. So they did all this study in measuring and understanding the Jalosinski Moria, its role in stabilizing this order and determining the order, etc. Okay, so I refer to you to this paper or to Andrei if you want more about that. So now I'm going to discuss on the other counterpart, which is the x equal 1/3, so-called x equal 1/3. So it has this formula there. And here the Kagome lattice is distorted. So we have now two different copper sites. One of these, so if we just look at one layer of copper, which is represented here. So the dots are copper, and there are two dots because there are two sides. So the red ones and the orange ones. So one of the copper sites, the red one, they make perfect hexagons. And there are two kinds of other hexagon made by the second copper site and a mixture of the two copper sites, let's say. Okay. So it's a bit more complicated model. It takes some time to get used to it, but it's quite nice. I like it quite a lot because if you look at just one layer and one perfect hexagon, you will see that the distortion actually still, beside the distortion, we still have six-fold symmetry around this hexagon. Namely, these triangles there, they are connected by a six-fold rotation. Okay. So it's distortion, but it retains some quite high symmetry. So I'll tell you a bit more about that later. So let me first show you some initial characterization of the material. So this is here. I should maybe speed up a bit. This is here the susceptibility versus temperature. It shows Curie-Weiss behavior at high temperature with fairly large 100 Kelvin antiferromagnetic interactions. And at low temperature, there's a separation of field-cooled and zero field-cooled with a maximum around 2.5 Kelvin, likely from some magnetic transition there at this temperature. And actually, in the heat capacity, you should look at the blue points there. There is a strong, very nicely resolved strong peak at this same temperature. But in the heat capacity, there is also additional feature. Here you see there is a double structure around 33 Kelvin, which you don't find here. So it's probably, it's certainly structural in origin. And beside, if you look at thermal expansion, there is, they are not there, okay. If it would be possible to just move the black box there, okay. Okay, I'll tell you what you should see behind. So there is in the thermal expansion, there is a signature as you see in the heat capacity, but there is also actually a small peak that is behind there at about 13 Kelvin. And that has no counterpart in the heat capacity and neither on the susceptibility. That's from me actually. That's from me. That's not. Yeah, great. Thank you. I thought it was from. No, that's not from me. It's not a big deal. It's not a big deal. Well, imagine there is a small peak there, resolved there at 12K. Okay, I'll tell you more about it. So what can we imagine for the magnetic model? Here we are helped a lot by the theoretical study of the colleagues, and including in particular the first principle calculation from Harald. And from this this calculation actually turned out that the important interaction are only the nearest neighbor ones. The other ones are much, much smaller, like percent of the main one. So there is no interlayer coupling and there is no further intralayer coupling either. And so the main interaction are related to the free distance that you have there. Two are more or less equal. I should mention that J and J prime are symmetrical, actually. So you can exchange them as you wish. So two of them, the one on the perfect hexagon and one of the links are of the same order of magnitude, 150 Kelvin, and the other one is actually found to be very small. So we end up with this kind of perfect hexagon linked by one double bond like that just in one direction. Okay. And they are all anti-ferromagnetic, yeah. That corresponds to what we can know from the angles also, that what we would expect. And the hierarchy is correct also with the angles. And further in this theoretical paper, they computed the phase diagram at the classical level. It looks like that. Yttrium-kapellasite is predicted, so that's where it should lie with two different structures, but okay, I don't go to the detail. It should be around here. So it should be in this one-third long-range order phase, which I will describe further. And so there's a phase that is symmetrical here, and here that's a more trivial phase when frustration is is suppressed, basically. And interestingly, at the center, so at the center you have the isotropic Kagome point, and you have also an extended regime where you have a so-called classical spin liquid, which to me is still a bit mysterious, but there are states where there is a large degeneracy of the ground state, but it's a discrete degeneracy. So these ground states are not connected as what I was showing for the pure Kagome case. It could be called jammed spin liquid in relation to previous studies. Okay, so let me go to a bit more into detail first. Before going to magnetic order, let me discuss the structure and distortion issues associated with 33 Kelvin peaks. So this is neutron diffraction, which, and in neutron diffraction, actually, we did study from high temperature down to 65 milli-K, and on the whole temperature range, there is no additional Bragg peak, so no change of symmetry, and no signature either of magnetic order. Okay, what we could see is a strong change of intensity of the structure factor at 33 Kelvin. And from the refinement, this was interpreted as actually there are tiny changes in the structure, which are mainly changes in the position of the deuterium. Here the scale is really extended. It's 2% change in the parameters, in the coordinates of the atoms. So if you have very good eyes, but I don't think you can see, if you look at the white dots here, which are the protons, you can see when you go to 20K, they change a little bit, and the other atoms, they basically stay the same. Tiny reorganization of the hydrogen atoms. So we wanted to have a closer, more local view on this problem, and we did chlorine NMR. So in the high temperature structure, we expect two chlorine sites. One sits at the center of the hexagon and one at the center of the triangles. And this, and both chlorine sites, they are not in the plane of the coppers, they are out of the plane. So here is the central lines, and we see two well-defined narrow peaks, which mean well-defined structure, very little disorder, and with the ratio we expect for the two sides, so that's perfect. Chlorine is spin-free half, so it is quadrupolar active. It has a quadrupole moment, and it's sensitive to electrostatic environment. So we expect not one line for one chlorine site, but actually three, 1 plus 2 satellites. And indeed, we do see, so this is the central line that is here. This is a zoom of this central line. And on each side, you have 2 pairs of satellites corresponding to the 2 sides. So that's textbook. That's what we expect. Okay. So now when we lower the temperature below 40 Kelvin, in between 40 Kelvin and 30 Kelvin, so the line moves as the susceptibility, and then the line shape changes. So first, both on triangular side, hexagonal side, whether the central line or the satellite, we do see some changes. For instance, if I look at the hexagonal side here, it broadens and even splits into different lines, or at least 2. And so we can follow it also on the satellite. Here it's the evolution of the satellite, and that's the width of the satellite. There's a clear change at 33 Kelvin at the structural transition, and there's a subsequent change here at 12 Kelvin, 13 Kelvin, which is where there was a peak that you didn't see on the thermal expansion. So indeed, there are structural changes, and in nature, the picture is different than the one from the neutron. From the neutron, there was no change at all of symmetry, so we should still expect 1 hexagonal side. And 1 hexagonal side gives 1 line, not a splitted line like that, which are 2 sides. So from the local point of view, this picture is a bit more complex. It seems that the small distortion, the small change of the hydrogen position is actually giving different kind of hexagon, but there are no spatial correlation between this distortion, and on average, the symmetry is maintained, basically. Okay. If we want to quantify a little bit this distortion, we can attribute the splitting to a change of the EFG, the electric field gradient, so the electrostatic structure around the chlorine by 5 degrees at 10K and additional 5 degrees at 10K. So there are probably small change, but with some kind of disorder, you would say, with no correlation in the plane. Maybe I will skip that. We make use of the fact that there are 2 chlorine isotopes actually with 2 different quadrupolar moments. So by looking at the splitting of the line for the 2 isotopes, you can decide whether the reason for this splitting is quadrupolar in origin, structural, or magnetic. And it turns out that it fits well with a structural transition, which was expected already from thermal expansion and heat capacity. So this is summarized here, this NMR study, that's the relaxation measurement. On both sides, we do see a clear, very narrow peak at the first structural transition, 33 Kelvin, then a broad peak of relaxation at this second transition around 15 Kelvin, 13 Kelvin, let's say. And then at low temperature, I'm going to discuss that now, we have a magnetic transition there. Okay. So let's go into the magnetic order. So first, with μSR, we checked that the sample was fully ordering. So here you can see that there is a large change of asymmetry versus time when we go from 2.3K in blue to 1.9K in red, basically. So it's a very sharp transition. There is a peak in the relaxation rate at 2.1 Kelvin, so where we have a transition. This is the frozen fraction, which is going to 1. So the sample is it's one phase, one magnetic phase below 2.1 Kelvin. Okay. This is the order parameter. I will not dwell too much on that. So that's just the frequency of the oscillation. So that's the internal field, basically. So that's the order parameter for the transition. From the value of the internal field there, we can estimate the frozen moment, which turns out to be quite small. It's only an estimate because we never know exactly where is the muon sitting. So and how how many coppers it's coupled, etc. But basically, it will be a small moment below 0.1 μb, which may explain why we didn't see magnetic Bragg peaks in diffraction. This I will skip. And for NMR, now if we look at the NMR at low temperature, so this is at 2.8 Kelvin here. Actually, at low temperature, the line broadened, and we don't see anymore all the details I was showing, the splitting of the lines from the structural transition, etc. It's all smeared out. The lines have broadened too much, and now the spectrum is somehow more simple. We have again two broad lines, one corresponding to the hexagonal side and one to the triangular side. So these are these two, and both are overlapping also because they have broadened a lot. So the first peak is attributed to the hexagonal side and the second one to the triangular side. And so across the transition, there are marked change. Actually, the hexagonal change that the hexagonal side does not change too much. Here, that's the increase of the change of the width of this side. There is something, but it's an increase by 20% of the line. But the triangular side is changing a lot with drastic broadening, and also it looks like we have now in the ground state we have different sides in the magnetic state. So this is the evolution of the line width of the triangular side. So how do we understand that? We can try to compare with the spin texture that was proposed theoretically, which is a bit complex, but I'll try to okay, I'll go a bit fast. But now we have the perfect triangles. So the model is made in the limit where J prime equals 0. So there is one bond missing everywhere on the lattice. So on each perfect, so now we have three different perfect triangles, the blue, red, and green. But for the local probe, they are the same. Actually, it's the different orientation of the spins. And the interesting point is that if you look at the center of one of these hexagons, any of them, of the perfect hexagon, the hyperfine field will be 0. Because we have two sets of three spins which are nearly anti-parallel. So the sum of the spin is basically close to 0, so the internal field at the center will be 0. And that fits nicely with the fact that the hexagonal side is not changing much through the transition. Now, for the triangular side, the situation is completely different because if you look at one triangle, so the chlorine sits at the center of this triangle, of one of these triangles, and now we have two spins which are nearly anti-parallel, like let's say these two ones, and there is another one which is not compensated, and that's the same for all the triangles. And now there are three different triangles because there are three different orientations of the uncompensated spin. So this could indeed give rise to maybe three different peaks that we can see there. Unfortunately, we don't have, we would need the total hyperfine tensor for this chlorine side to be able to make a quantitative comparison, and that I could give you the moment that is responsible for that. So this I cannot do. I can just say that at the qualitative level, it fits with the theoretical prediction. Okay. Yes, Carlo?
Is it right that actually the hexagons are unfrustrated and the only source of frustrations are these huge hexagons made out of how many? 9 spins?
You could see it like that. But these guys, they are not fully isolated. I mean, I would have to. Okay, I never thought about it like that.
Okay, right, sorry. Yes.
Thought about from that. Yeah.
orders of?
Yeah, I will actually tell you more about that. So from the ab initio calculation, so the main coupling are the ones that are there actually. So the one on the hexagon there, the one that is leaking 2 hexagons, and the third one is 0 or small. Okay, that's why it's not there on the drawing. But the picture, I will finish by showing you inelastic neutron scattering, and we have refined somehow these values. So I'll go a bit 35 minutes, something like that. So this is as of the dynamical structure factor at 60K, 5K, 1.5K, and at low temperature you see clearly emerging what is identified as a spin wave, which are at the K points, so which are compatible with, here it's written 1/3 order that is proposed theoretically. Interestingly, if you look at the dispersion along C in the 0,0L direction, it doesn't disperse at all. Actually, there are flat roads of intensity, so there are hardly any correlation between from plane to plane. Here is an attempt to integrate the signal in the elastic channel, and there may be, but it's really just at the limit of the noise, there may be small bragg peaks at the K points, but it's really at the limit. So in any case, the magnetic moment should be very small. And that's to answer your question, that's the simulation of the spin wave dispersion. So that's Edwin Kermarek did that, and he actually took a model that is very close to the one that was proposed initially, but we need to reproduce the feature of data. We need a J prime that is finite, that is not 0 or not very small. It's actually close to half the over J's, and it's slightly distributed also, or it's distributed. Okay. And with that, so now from this data, the new location of Y-kapellasite would be there, so closer to still in the 1/3 phase, but closer to the spin liquid, classical spin liquid phase. Okay. And with that, I should conclude. So let me briefly summarize. So we observed the long-range order with a spin texture and wave vector that are compatible with the theoretical prediction for the nearest neighbor model. We observed a very small moment, probably related to the proximity to the boundary between the two phases. What I did not address, and because we didn't study it so far, is the role of disorder. So what I showed you is that there is some structural issue, but they seem to be small and probably they don't affect the magnetic model. Now I didn't explain, but the formula I showed you is actually charge unbalanced. There is a proton that is missing somehow, so there has to be a bit of this substitution on some site, like the chlorine site. I mean, some dilution of this site to maintain the charge, and this is not resolved. So that could be a source of disorder and explain maybe the distribution of the J that we observe. I didn't discuss at all, and it was not studied at all, what is the role of Jalusinski-Moria in this picture. It's probably there because it's there in the x = 0, so I don't know, it has to be measured and the effect has to be investigated. I should mention that there is another synthesis of this phase that leads to compound which is a bit different with 2 transition and one at 11 Kelvin. It could be a phase mixture with the x = 0, but that has to be clarified. There are other compounds now replacing chlorine by bromine, which may help spanning this phase diagram. And on a more maybe theoretical view, well, I think this phase still has to be investigated, maybe in the quantum limit, and even this boundary when you add the quantum fluctuation, it may be interesting to see what's happening and what kind of moment value, for instance, we would expect. Thank you very much.
Thank you, Fabrice, for walking us through the state of the art on the Kagome. Questions, Carlo?
Can you differentiate between the ordered moment on the hexagon and that in between the hexagon?
Well, since we don't have the Bragg peaks, etc., not from neutron, that would be the way. In principle, from NMR, we should, if we would know perfectly the hyperfine coupling for both sides, etc. In principle, we could. It's not an easy task. But,
Hi, Fabrice. Thank you for the nice talk. So this order that you have shown us is essentially different, right? I mean, from the x equals 0 phase.
Yeah.
It's very different.
It's right? Not q equals 0. It's 1/3. You have you see that the magnetic lattice now it's completely different. Huh? It's free. It's multiplied by 3. You know.
Well, my question, I guess, is there we attributed magnetic order, which was special one, yeah, with selected chirality. Probably no, right? We attributed that to Julius-Maximilians-Maria interaction. So my question would be, do you have a feeling, at least, I know it was not studied yet in this case, but do you have a feeling how important this could be in your case for selecting this particular order that you see? Well, you were not able to characterize it very well, I guess, but still.
This order, you get it without Julius-Maximilians-Maria. Okay.
Yeah, I understand that.
What we saw is compatible with that, let's say. So it seems that at this stage we don't need Julius-Maximilians-Maria. Now, naively, I don't see why Julius-Maximilians-Maria should be very different than in the x equals 0 case, because the bond angles are nearly the same. The chemistry is very similar.
Yeah, exactly. But I can tell you that the IISER, for instance, gives you really the same, basically, lines. The same width. So it should be of similar order than there. And then I wonder how important it would be here, because there it was shown to be, I mean, really large, you know?
Yeah.
So.
And so this is clearly something that has to be investigated. Now, I'm a bit surprised that the spin waves are gapless. Big specialist of that, but with such large jealousy, I don't know how it was. I don't remember how it was in the x equals 0 case. But with such large Julius-Maximilians-Maria, I may expect.
Yeah, we didn't. Do this experiments. But we saw Bragg peaks there.
Yeah, that was a bit different.
Yeah, so it was different.
So yeah, it has. So I would say naively it should play a role. So far, we didn't see evidence for large anisotropy. But okay.
Okay, thank you.
I think there was one question.
A question from the online participants. Please unmute yourself and ask.
Yes. This is Masashi Takigawa. Can you show me the line width data again at two different chlorine sites?
Sorry, I didn't get it. This one? Or at higher temperature?
Temperature dependence of the line width. I mean,
at high temperature, you mean?
No.
At the magnetic.
Yes, this is. So the triangular site, the line width start to increase below 3.6K, which is quite different at the 2K ordering in hexagon or also mu-SR data. So do you have any idea, or is this caused by external field? Or?
Yeah, I think it comes from both. So we have a strong applied external field of 7 Tesla, which polarize. For instance, in the susceptibility, we see that this cups is mirrored out when we apply strong field. And for instance, the nice field-cooled, zero field-cooled aperture that we have at low field in susceptibility is mirrored out at 7 Tesla. But probably correlation start to build up around 5 Kelvin. Around 5 Kelvin, you have this aperture of the field cooled and zero field cooled. The μSR, I can show it here maybe. Yeah, we have a bit of change of the dynamics, a bit above 2.1 Kelvin. That's in zero field. So I think that's mostly an effect of, I think the correlation really starts below 5 Kelvin, and on top of that, you have the effect of the external field, yes, indeed.
Oh, I see. But the muon relaxation rate had a very sharp peak at 2K.
It's much sharper in zero field, yes.
Okay. Thank you very much.
Any more questions from the online or physical participants here?